All right, so today we're going to take a look at logarithmic and exponential functions. Starting with logarithms, they take this form, say that log of a x equals y, or equals f of x. And this implies that the a to the y equals x. So what we're saying here, if we look at the parts of this function, of this notation, we have log, we have a subscript of the base of the logarithm, and then we have our variables, x and y. And when we write this, it means this. So basically, log of a of x equals y means we have solved this equation where y was an exponent. All right, so there's three types of logarithm we can use. Now, technically, a can be any real number. But really, only three numbers are in common usage. Logarithms can be in this form, this form, this form. So there's logarithms of 2. These are binary logarithms. Right, so if I say log 2 of x equals y, I end up with, using this formulation, 2 to the y equals x. So this gives you binary numbers, where as the exponent increases, you go up by powers of 2. Log of 10 to 10x, same thing, you just put the base here. Y equals x, or log of e x now this will just be written as log of 2. When we're talking about binary, this will use the standard form. This is called the common logarithm, and this is the natural logarithm. So these both have special notations, and by special I mean this one will just be written without the subscript. If there's no subscript in this notation, it is assumed you mean 10. This one will be written as this. So instead of using the notation where you say log for logarithm, I'll say ln, which is usually pronounced ln. Sometimes you say ln of x, or you say ln x. It stands for logarithm naturalis, Latin for natural logarithm. Now, why do we use these three particular ones when we can use any? Now, the book has plenty of examples on using any of them, and I'm going to ignore all of these because these are the only ones that you're actually going to see anywhere really in your life. And when we're talking about calculus preparation, it's a pre-calculus class, the one you're going to see very much is this one, the natural logarithm. So we're going to focus on that one, where we're at base e, and we're going to talk about why base e is important. It's going to lead us into the other part of this chapter, exponential functions. So what is e? E is called Euler's number, and it is a function in itself, an exponential function. It equals 1 plus 1 over n to the power of n, as n goes to infinity. So as the number, so obviously when n is 1, equals 2. Right? or this expression would be 2 when n is 1. There's a table in the book that shows that this quickly approaches so that e is approximately 2.82. Oh, I should have written that down because now for some reason I don't remember it. Sounds about right. But let me check because I left my book in there. Okay, so that's one of those things I should have been able to remember, but didn't. 7.1. Or 2.72, 2.7. Around here. It is like pi, a irrational number. You cannot express it fully as a decimal. And it's a because it's non-repeating. So we just give it e. Now, Euler gave it the character e because e is the first letter in the word exponential, and we often call this the exponential function. So rather than saying an exponential function, if we say the exponential function, we mean this function here, which has this value. This part here, as n goes to infinity, will be the first thing you encounter in calculus. And it will make more sense when you get into that. This is called the limit, and it's vital in defining the basics of calculus. So let's get back to what can we do with these things. Well, we have these logarithms, and logarithms clearly show us they are exponents where y is the exponent. So we use them to solve equations where we have this going on. So let me remove this, and we'll get back to what we can do. And I will do all of these calculations assuming the natural logarithm. So with the natural logarithm, ln of x equals y. This means that e to the y equals x. So what can you do to solve this kind of equation where you have, and this is all it's really for, is what do you do when you have y in the exponent and you need to solve for y? So what I mean is you need to turn this equation back into this one. And algebraically, what you do is you say, well, I can say that the ln of e to the y equals ln of x. Right. Same as I could multiply both sides by 1. I could multiply both sides by a common factor or divide by a common factor. I can multiply by a conjugate. I can take the logarithm of both sides. And when I do this, I have this form. So now I have ln e to the y. And I defined this as e to the y equals x. So what I have here, if I have e to the y equals x, this is my x value. I can define this as equal to or equivalent to the base raised to the exponent equals this. Right? So what I'm really saying here, if I say ln of e to the y, I put it in this format, I'm saying that I have right, because I have e to the y equals x. This is x. So I substitute e to the y in for x, and I get e to the y equals e to the y. Okay, that makes sense. Because what it means is a logarithm and exponential are inverse functions. It's the same as multiplying something and then dividing it by the same thing. So ln of e to the y is just y. And that's how you travel from here to here. Similarly, I can exponentiate both sides of this equation. I could raise both of these to the e. I could say e to the y equals e to the ln of x, which means I would get e to the y equals, these are inverses, x. Now, by using these inverses, there's a more complicated way I could show a proof. What I'm going to do is I'm going to write down some of what's called the laws of logarithms. And you'll see why they're actually more useful than they are complicated. And then I'll do an example of something we do with, say, an exponential or a logarithm on a semi-daily basis. So the laws of logarithms, there are three main ones. And that is three things that allow you to manipulate logarithms algebraically. I can say and I'm going to focus on the natural log. There's the natural log of a product, logarithm of a quotient, or the logarithm of an exponent. I already proved this one, showed you a little bit about how this one works. And what this means is because the term inside the logarithm is an exponent, we go to the rule of what happens when you multiply exponents. Well, if you raise an exponent to an exponent, what you're really doing is multiplying the exponent. So that's really what we're doing here. These are laws of logarithms are in fact the same as the laws of adding, multiplying, and dividing exponents, because they are exponents. So logarithm of the product a times b is the logarithm of a plus the logarithm of b. Natural log of a over b, ln a minus ln b. And logarithm of anything to an exponent is that exponent multiplied by that log. So now this allows us to more easily manipulate larger numbers in the pre-computer, pre-calculator era. We don't really need to do that so much anymore. But what we do like to do is use this concept to solve logarithmic or high-level number problems. So let's look at something we can do using logarithms and exponentials. Now I'm going to take this one directly from the book. And let me find the page number for you. Oh, it's here. Here we are. Logarithmic scales. I'm going to use the Richter scale. So there's one thing we can do. It's called logarithmic scale. And you can find this starting on page 381. It'll show you the pH scale, measuring the strength of an acid or base. But I'm going to move on to the Richter scale and use that as an example. So the Richter scale is how you determine a rating for the magnitude of an earthquake. And we say it that Richter scale has this form: m equals log of 1 over s. Sorry, I over s. So, what this is I is the intensity at 100 kilometers away from the epicenter of the earthquake. And S is what's called the amplitude of a standard quake, which is 1 micron, equals 10 to the minus 4 meters. And this is, if we take S and say this is the amplitude of a standard quake, if the intensity is equal to S, we have M equals logarithm of S divided by S, which equals the logarithm of 1. Now, remember, these are exponents. So what is the logarithm of 1? The logarithm of 1 is 0. Why is the logarithm of 1 0? Well, if I were to graph a logarithm, I could go point by point, and I would show you a scale that looks a little bit like this, where I calculate x versus y, recalling that y is the logarithm of x. So this is log versus x. And I would get this. Or that's the x-intercept, log 1. And if we were to take this back, and I put this in the form that I originally described, I said log of A so this is A to the y equals x. In this case, A is 10. And what the rate what power do you need to raise 10 to get to 1? Well, you have to raise it to the 0 power. Anything raised to the 0 power is 1. So the log of 1 is 0. In this case, this is the common log for base 10. And that's what is used in Richter's scale. So this is useful, and this is useful because what it means is the magnitude of an earthquake. And from 1900 to 1950, Richter measured a bunch of earthquakes. And he had the largest one with a magnitude of 8.9, and the smallest one was a 0. Now, this is a ratio of about 800 million. So a 0 on the Richter scale is nearly 800 million times less intense than 8.9. So rather than having to say the magnitude in regular numbers, so it's much easier to say, well, that was a magnitude 5 earthquake or that was a magnitude 6, rather than it is to say that was a magnitude 830 million. And that's really the use of the scale here. It also lets us know that in this case, because we're in base 10, every increment is 10 times greater than the last. So this means that a magnitude 1 is 10 times an m0. And m equal 2 is 10 times an m1, and so on. That means an m8 is 10 times an m7. So it lets us keep the number on a rational human scale, while also including the fact that the intensities of these are massively different, because they're going by factors of 10 rather than linear increments. Now, let's look at an exponential function, or let's look at the exponential function and see what we can do with that. This one should be a little more clear. If we talk about the exponential function. So this has a graph where it looks like this. And you may notice, if I were to graph the logarithm on the same scale, there would be a few things from graphing that we can go over here. So we can say and I guess I'll write them down, right? So we can say the domain of e to the x, so properties of e to the x. Domain is all real numbers. Range is 0 to infinity, and therefore it has a horizontal asymptote at y equals 0. That is to say, this at negative infinity, e to the x equals 0. Since we'll never get there, we say that y equals 0 is the asymptote. And these opposite things are true for our logarithms. Logarithm has a vertical asymptote at x equals 0. It has a domain of all positive numbers from 0 to infinity. It has a range of all real numbers. These functions are symmetrical around the line y equals x. This is y equals e to the x and y equals 1 of x. So the exponential, and I told you it had a form. It has the form t equals 1 plus 1 over n power of n. As n approaches infinity. So what do I want to do with that? Well, the first thing that comes to mind usually, thematically, is when talking about interest, compounded interest. It's the basis of our economic system, so it comes up an awful lot. And it is on exponential growth, so we're close. Didn't have the page number written down, so let me write down what it is, and we'll go through how an exponential helps us with it. So let's talk about compound interest. Compound interest has this form. Function a of t, where a is typically taken to be the annuity, equals the principal, however much you start with, times this factor, 1 plus r over n to the power n times t. Where in this case, equals the starting amount. So you can also say the amount with respect to time. R is the rate, so the interest rate. So if you have 1%, 10%, 18%, etc., that's R. N is the number of time periods. And T is in years. So it's or months, or it's the time period itself. Now, if we want n to get very, very large, that is to say, we want to let n go to infinity, and we want to make our lives a little bit easier and let m equal n divided by r, we can rewrite the equation as a of t equals the principal times the factor 1 plus r over n. All right, so we still got this part. I'm going to break up this exponent, and I'm going to call it n over r times t. Right? All I've done is I've multiplied the exponent over t. So I've taken n times t equals n over r times t. So I've just multiplied by r over r, which is 1. Now, I've made this assumption. So I can change a variable. I can say that t equals 1 plus r over n. M is n over r. This is 1 over m. Right, so I can say that n over r equals 1 divided by r divided by n. Substitute here. I have n over r is m, r times t. Well, 1 plus 1 over m to the m is identical to 1 plus 1 over n to the n. So this is e. I can say that this is p times e to the power of rt. Or, spread it all out, and finance, this is just often called A part, as in A equals P to the ERT. And this is when interest is compounded continuously. And this is when interest is compounded, say, daily, monthly, yearly. Now, interest is really calculated this way now because you can continually recalculate it using computers. And the way your bank makes money off of you, if back in the days when they gave you an interest rate, is because they would compound your interest rate hourly or daily, give you that much, while the interest itself was really compounding infinitely, continuously, and there would be a difference in that amount, and they would keep that difference. They still do that, but now that your interest rate is so low, it doesn't matter. But this is an example of how we can take a known discrete function, something that's working every hour, every day, something that's working every instant of every point of time, and simplify it. Now, the other way it's simplified is if you look at these two things, and I say, okay, here's the rate, here's the time, I have to give you a number of time periods. You have to plug all this into this function. Or, if it's continuous, I just say all you have to do is press the exponential button on a calculator, and feed RT as its exponent. So you need there's less difficulty in doing this equation than doing this one. Now this particular exponential form, this is for continuous growth. So we're talking about compound interest. But it also works for anything that grows exponentially. So it works for the growth of bacteria. They have exponential growth. It works for radioactive decay, because that has exponential decay. So this equation is found in finance, in this form, but it's everywhere in biology, in physics, in chemistry, in determining the rate of something, how much you have left, or how much you'll have after a given amount of time. For instance, if you knew you started with a certain amount of bacteria, a sample, and then you knew how often, what the rate of their expansion was and how long you gave them, you would know how much was left. Or if you said, well, I started with, 1 gram in a sample, and I came back 2 days later and there was 3 grams, you could plug 1 into here, 3 into here, you know what E is, you know how many days it took, you came back, and then you can solve this to find R. So let's look at an example of trying to do that. And then that'll be it for today, because this problem will be an exponential equation, and we'll have to solve it using logarithms. Let's talk about exponential growth. And I want to say it's the same as before. I could say the mass over time equals the initial mass times E RT. So this is the difference I would give the form. And I'd say, okay, I have m naught equals 1 gram. And T equals, let's call it 2 days. And M of 2 equals 3. So what am I being asked to find? Well, I know that M of 2 is 3. I'm going to plug in the information I have. I want to find the rate. Find R. So let's plug some numbers in. Substitute M naught is 1. E is E. The R is 2. I'm trying to figure out the rate of growth in days. and I have this equals 3. So I have 3 equals e to the 2r. And I need to solve for r. I said r is an exponent, so I need to use logarithms to find it. So I will take the natural logarithm of both sides. I'll use the natural logarithm because I'm using the exponential function. I'll say ln 3 equals ln of e to r. Right. So I have ln of 3, ln of e, wash is 2r, or ln 3 2 equals r. Now I can then grab a calculator and try to plug in the natural log. So certainly, even a scientific calculator. I don't know if you can see it here. Right there is the natural log button, and if you were to hit second, it would become the exponential button. So we can hit, and this calculator has both a natural log button and a log button right above it of 10, which could give you 10 to the x. So if I say ln 3, I divide that by 2. So the natural log of 3 is approximately 1.0986, but I'm dividing it by 2. And this gives me my rate is 0.549. So this is my rate of growth per day. So every day, my sample, in this case, if I started with 1 gram and I ended up with 3 2 days later, it meant that every day I experienced a growth of this much. So after the first day, instead of being 1 gram, it was as 1 plus 0.549 grams. And then that gave me 1 plus 549. And then I got, on the second day, another amount of this amount of growth. That's what this equation is telling us. There's my rate of growth. I could also say it's 0.55, depending on how many significant figures I was keeping. Generally, 2 or 3 is fine. And we're talking this level of growth. And it would depend on how fine these measurements were, right? If I said I started off with 1 gram, if I knew it was 1.0 grams, or if I knew it was 1.00, I knew that this came out to 3.00, I would know that 3 digits is fine. But chances are 2 would be acceptable here. So that is an example of how logarithms and exponentials work together. So keep this in mind. If you have questions, email me and take a look at the upcoming assignment, and there'll be a bunch of stuff like this for you to manipulate. So that's it for today. Thank you for watching.